Why is the Einstein Telescope a triangle when most other interferometers are 90-degree angles? Typically, when you see a gravitational wave detector like LIGO, they are a 90-degree corner because of how interferometers work. So I explained a little bit about how interferometers work in my overview video of Einstein Telescope and ETpathfinder, but I'm going to explain it again quickly because we're going to be getting a little bit more in depth. So the basic idea of how an interferometer works is that you have the two arms, and at the end of either arm there is a mirror. And there's also a laser that is split into two beams that then hit the mirrors and then come back. And when they come back and interact with each other, they create an interference pattern. And from this interference pattern, we can tell the distance between the mirror and the sensor, and that is because the speed of light. So we know exactly the speed that the light is traveling, we know the phase of it, which is, like the sine wave kind of deal, and so from the way that they're interacting together, we can tell what the two different distances are because of the way that they have interacted and the pattern that they create. And so when a gravitational wave then comes by, it either compresses or extends the space between the mirror and the sensor. And this affects the distance that the laser travels, so it then affects the phase that it is arriving at the sensor. So it changes the interference pattern that we can see. And so when the interference pattern changes, we know that a gravitational wave has affected the telescope. Now, more specifically about the movement, gravitational waves tend to have two different polarities or directions of movement. There's plus and cross. Plus is that the space gets stretched vertically and compressed horizontally, and then it goes vice versa, of where it's compressed vertically and stretched horizontally, and it alternates between the two. The second is cross, which is the same, just at a 45-degree angle. And a 90-degree interferometer can pick up these polarizations, but they can't really pick them out from each other, so they really only see a combination of these two polarizations. And you lose some information then about, that you could get of more information about how they were exactly formed, like what kind of event it was, because you don't really know which polarization is the stronger one per se. This is part of the reason why Einstein Telescope is a triangle. So it is multiple interferometers that are then at 60 degrees, and they're all nestled in together. And you should be able to actually separate the polarizations from each other, because similar to kind of like algebra, when you have the system of equations and they have like x and y and all the equations, and you can do like a whole bunch of flipping around to be able to solve for x and y. And that's basically what this is that they're getting a whole bunch of more data so they can solve for the polarizations. Also, the triangle shape is great for maximizing the amount of space that they're using. So since all these interferometers are all nestled up together, you're going to have two arms right next to each other. And so when they're going to be digging out the tunnels to put the interferometer in, they can have double the amount of data for the same amount of distance that they are digging out. So this is also great for cost because you're not digging as many tunnels, as well as it's also minimizing environmental effects, because that is something that is always important to look at and be aware of when building these types of projects. Another quick side ending note is that it's actually not just 3 interferometers in the system, it is 6. That is because at each corner there's going to be 2 interferometers, and they're going to be right next to each other. And what the differences between them is the laser wavelength and the material of the optics that they use. So one of them is going to be a 50 nanometer laser with the crystalline silicon mirrors and a cryogenic system, while the other one is 1064 nanometers for the more typical fused silica room temperature. I did another video about all of the different, the 2 different materials and comparing them and what all is going on with that. So if you're more interested in that, go and watch that video. But the reason why they're doing this is it gives them some more data, because it gets some different stuff kind of going on with the frequencies and being able to measure more frequencies, and it'll be really important to be able to get the best data that they can. They're going to get so much data, which also, I can imagine how crazy that data analysis is going to be. That code is going to be so many pages, which I did my own long code with data analysis, and that was just with a single part of this. So, yeah.